This lecture is about resonance and predicting chemical reactivity using resonance. What is resonance? Resonance is a model, an approximation, used to describe the bonding in molecules. And because it's an approximation, it doesn't work all the time, but it does work for many different examples in organic chemistry. Alternative plausible Lewis structures are resonance structures. So if you look at the example in the middle, the first structure is what you would normally draw for this molecule. It has the right number of bonds, everybody's got an octet, there are the right number of lone pairs on O and N. But if you look at the representation of the pi bond as two red dots, we could say that in an extreme situation, maybe the pi electrons are actually now on the oxygen. They're a lone pair on the oxygen. And the poor carbon atom now doesn't have an octet because oxygen stole its electrons. So we would say that that first structure resonates to the second structure, and we would represent that by a double-headed arrow. Now, this is an extreme situation. We don't have a pi bond. Carbon doesn't have an octet. There's charge separation. What gives here? Well, this isn't the real molecule. It's a characteristic of the molecule, like an excited state. So we need to incorporate it to completely describe the molecule. If we don't, then we won't understand how the molecule acts when it is in an excited state, when it is chemically reactive. So it is important that we use this in our full description of the molecule. Now the second structure resonates to the third structure by the lone pair on the nitrogen forming a pi bond with the carbon. Now everybody's happy. We have a plus charge on the nitrogen in this case, and we still have the minus charge on the oxygen. These three structures are simply the same molecule. There are different electronic descriptions, different Lewis structures, but it's the same molecule. They're all resonance structures of one compound. Now, when you're drawing resonance structures, you have to leave the sigma bonds alone. That's the primary framework of the molecule. You don't break the sigma bonds, and you don't make any new ones. If you do that, you're either doing a chemical reaction or you're making a new isomer. None of those are resonance structures. Now, what is the real molecule? We can say that it's the average of all of those resonance structures that we drew that are plausible. We call this real molecule, which I do put in quotes because, of course, it's still an approximation. We call that the resonance hybrid. So, based on our three resonance structures, we note that the double bond exists either between C and O or between C and N. So that means our pi bond is spread between O, C, and N, and we can represent that by a dotted line. So that means that there's no real strictly double bonded character between C and O or C and N. There's partial double bond character between C and O and C and N. As far as charges, the first structure had no charges, the second structure has a plus on C, a minus on O, and the third structure has a plus on N and a minus on O. So our plus charge is partial. There's a little plus charge on C, partial positive. There's a partial positive charge on N. And the only atom that gets a partial negative charge is O. So that's our resonance hybrid. Now that resonance has been defined, let's look at the different types of resonance. First, we have breaking a polar pi bond. And what that means is you have a pi bond between two atoms, X and Y, and Y is more electronegative than X. This is that extreme situation where you're breaking the pi bond, which you see there, the two dots for the electrons, and you're moving both electrons to Y as a lone pair, giving less than an octet on X, so in this case I'm going to give it a plus charge, and a negative charge on Y. So if you look at the example, it comes straight from the previous slide. You have the pi bond breaking, electrons flowing up to the oxygen, giving it a negative charge and a lone pair. and a plus charge on C. So Y is O and X is C. Then our next type of resonance is what's called lone pair empty orbital resonance. So you have X with a plus charge, and that represents an empty orbital, you see in green on the right, next to Y with a lone pair, and the lone pair is being donated to the empty orbital. So you can show an arrow from the electrons that are red going in the middle, because they're going to be shared between X and Y to form a pi bond. Our green representations show the orbitals, and again the empty p orbital is overlapping with the lone pair. The electrons are being shared to form a pi bond, represented on the far right as two p orbitals overlapping, and the two red electrons are being shared between them. So we've seen this before too. Our example shows that X with a plus charge is the carbon in the middle of the molecule. Y with the lone pair is the nitrogen, and they form a new pi bond. Empty orbital pi resonance involves an atom with a lone pair, X, in this case I'm giving it a plus charge, adjacent to a pi bond between Y and Z. The two electrons between Y and Z flow toward the plus charge on X. Right? That plus charge is acting like a vacuum. It's sucking the electrons from Y and Z toward X. And that flips the pi bond over so that it's now between X and Y. And now Z ends up with the plus charge. It has the empty orbital. So if you look at the green representation, there's our empty p orbital adjacent to our pi bond. Note how all the orbitals overlap. They're all parallel. This is going to become very significant when we describe a geometric requirement of resonance later. They have to be parallel overlapping orbitals. So you see that empty p orbital is pulling on the electron density from the pi bond. That shifts the position of the pi bond from being between Y and Z to being between X and Y. So you can see that the electrons simply flow over and end up between X and Y. So now you have a pi bond there and an empty orbital on Z. So in our example, you have a plus charge on the carbon adjacent to a carbon-carbon pi bond, and the pi electrons now flip up, leaving the plus charge on the end. X, Y, and Z in this case are all carbon, and that's always going to be the case. And the reason for that is that carbon can be less than an octet, but you can't do that for the more electronegative atoms such as N and O. So X, Y, and Z will always be carbon for this type of resonance, empty orbital pi. Now lone pair pi involves having a lone pair on atom X adjacent to a pi bond between Y and Z. Now we're not pulling the electrons toward X, we're pushing the electrons so that the lone pair on X pushes electrons from the pi bond onto Z. So X is donating its electrons between X and Y, forming a pi bond that knocks those electrons that were pi bond between Y and Z out onto Z. You can also think of this as I've got a lot of stories for this, but one of them is the idea of two people jumping onto a trampoline and knocking two people off the trampoline. Or, because I live in the city, you've got two people who are scary looking coming on a bus. They're going to sit next to you and your friend who are sitting on the bench, which is between Y and Z, and you guys get scared and jump up, holding on to the handrails instead when they sit down. So the two scary guys are between X and Y, and you guys were between Y and Z. You jump up, and now you're on Z, which is the handrail. Okay? Now in the green representations, again, you see that the orbitals are overlapping. They're parallel. There's the lone pair on X next to the parallel pi bond between Y and Z. The electrons, again, are going to be pushed in between X and Y, knocking out the electrons between Y and Z, so that you get a pi bond between X and Y, shared 2 red dots, and then 2 red dots end up on Z, the lone pair. So in an example, the oxygen atom is X. It creates a pi bond to carbon that knocks out a pair of electrons between the 2 carbons, that pi bond, so that that lone pair ends up on the terminal carbon as a negative charge. X, Y, and Z can be anything in this scenario. Doesn't make any difference what it is. Electronegativities do not have to be greater, smaller, doesn't matter. They can be any atoms. So, just as a refresher, oxygen is X, and in this case, 2 carbons are Y and Z. But they could have been any other types of atoms as well. Unpaired electron or radical pi resonance involves atom X having just one dot, one electron, which is called a radical, adjacent to a pi bond between Y and Z. Now, X doesn't need 2 electrons in order to form a pi bond, it just needs 1. So only 1 electron is going to come from that pi bond to create a new pi bond between X and Y. We can represent that with arrow notation using these fish hooks that, notice, don't have 2 prongs at the end of the arrow in the description of electron flow. They just have 1. And when these fish hooks get together, one from X and one from Y, that forms the new pi bond. And another fish hook arrow goes towards Z, giving that the unpaired electron. So in the green representations, you see that we have the unpaired electron or radical as a p orbital, and it's adjacent to our pi bond. The electrons slide over to give our new pi bond between X and Y, breaking the old one between Y and Z, and now Z at the end ends up with an unpaired electron. In our example, you have a carbon atom with a radical next to a carbon-carbon pi bond, and we flip the pi bond up so that the carbon radical is at the other end. These are actually what we'd call 2 equivalent resonance structures because they're structurally identical, which makes them equally likely to contribute to the nature of the molecule. We'll get into that in greater detail. So in our case, X, Y, and Z are all the same type of atom, but X, Y, and Z can be anything. Now, our last type of resonance is benzene resonance, represented by benzene, as seen there, 6-sided ring with 3 alternating pi bonds. The idea of benzene resonance is that the pi bonds are flipping around in a circle, so they change position. The reason this occurs is that you've got, as shown in green, overlapping p orbitals, so that you really can't tell where the pi bond is, and therefore it just spins around the entire molecule and blurs, spreads out the 3 pi bonds over the entire structure. Thus, in the typical drawing of benzene, one will place a circle in the middle of the 6-sided ring to represent that type of resonance hybrid that you would get from benzene resonance. This type of resonance makes benzene extremely stable, which we call aromatic. So stable, in fact, that in Organic Chemistry 1, we don't do any chemistry with benzene. We basically treat it as if it's untouchable, almost like the noble gas of molecules. But in Organic 2, we mess with benzene all the time. So here's an example of something which is analogous to benzene, pyridine, and we flip those pi bonds around to different positions, so now they're all switching positions, and that represents benzene resonance for pyridine. Pyridine is very stable, just like benzene. It's considered to be aromatic. Okay, warning, warning! These are the things you should never do. Never put a plus charge on a carbon next to a minus charge on a carbon. It's ridiculous. All they do is make a pi bond. If you have a cation, plus charge, or an anion, negative charge, okay, these are what the molecules are, only use the resonance that moves the plus charge for a cation, or the minus charge for an anion. You don't create any new charges. So for example, if you have this anion and the lone pair is on the carbon, you do not do anything other than move that lone pair using lone pair pi resonance up to the oxygen, put a negative charge on the oxygen. That's cool. That's perfectly acceptable. That's correct. If you, however, decide, hey, I've got a carbon-oxygen pi bond. Isn't that a polar pi bond? I'm going to break that and put the negative charge on the O and a positive charge on the C. Nope, that's wrong. That's wrong for two reasons. One, you violated the rule that you shouldn't have a plus carbon next to a minus carbon. They should just make a pi bond. Also, you've added additional charges and you started off with a negative charge. And all you were supposed to do is move that negative charge around. So for two reasons, that structure is wrong and you're not supposed to draw it. In the cation example, you're never supposed to take that lone pair on that oxygen and do lone pair to pi resonance, because if you do that, you'll have a negative charge next to the carbon, which is wrong. You'll also have additional charges, an additional plus charge on the O and minus charge on the C. So the only correct way to draw resonance for this cation is to do empty orbital pi resonance, pulling the electrons from the pi bond toward the cation, moving the plus charge next to the oxygen, which then resonates to the oxygen via the lone pair on the oxygen going toward the plus charge. So there is no way that you can generate additional plus and minus charges when there's already a charge. You never want to put a plus charge on a carbon next to a minus charge on a carbon. Using an example, let me show you how to draw multiple resonance structures. First thing you want to do is put the lone pairs in all the atoms that should have lone pairs. Next, we're going to apply one of the types of resonance, and you can see there's a C double bond O, so I'm going to break a polar pi bond. Give a plus charge on carbon and a minus charge on oxygen. Now we have an empty orbital that can resonate with the adjacent pi bond, so we get empty orbital pi resonance. The plus charge on carbon acts like an electron vacuum. It can suck the pi electrons toward it, which will cause the plus charge to now be next to the nitrogen. Now we have a plus charge, which is an empty p orbital, next to a lone pair on nitrogen, so that lone pair is going to be sucked toward the plus charge and create a pi bond. Now notice that I've highlighted all of the different atoms involved in resonance in pink to distinguish them from the rest of the molecule that's not involved in resonance in your analysis. That way you're focusing in on exactly what you need to think about. It's called isolating the system. If you do that, if you circle that section or highlight it a different color, you won't be worrying about the rest of the molecule, and you'll be able to figure out what type of resonance you're applying in that specific part of the molecule. It's really the best way to think about it. It keeps you focused. Okay, we're not done with drawing all of the resonance structures. Even though we create a plus charge which moved all the way down to the end of the molecule, you might think we're finished, but you should always go back to the original resonance structure and see whether or not you can do something different, apply a different type of resonance. And in this case we can apply lone pair pi resonance. The lone pair pushes on the pi electrons, forcing them to get spit out onto the carbon. Another way of thinking about this is the idea of a trampoline. So someone jumps up on the trampoline, say two people, and then two people bounce off the trampoline. Two electrons bounce in, two electrons bounce out. So you get a pi bond on one side and a lone pair on the other side. With lone pair pi resonance, we can continue to push the lone pair from the carbon all the way up to the oxygen, but now we have the same resonance structure as before. So we really are done. There's nothing else for us to do. We've drawn all the possible resonance structures for this molecule. Practice problem 1. Draw all plausible resonance structures of each compound. Now remember, when you start to do the problem, make sure you put lone pairs wherever they're necessary on the molecule. Also, if a molecule is a cation or an anion, make sure that you just move that charge around. Don't create any new charges. Answers to practice problem 1. In part A, we have a neutral molecule, so you can get positive and negative charges in resonance. If you look at the C double bond O, that's a polar pi bond, so we can break it, take the pi electrons and bring them up to the more electronegative atom O to give it a negative charge and carbon a positive charge. Next, we can take that empty p orbital on carbon and we can use that to pull in the lone pair electrons on the oxygen, so that's lone pair empty orbital resonance, giving us a pi bond with a plus charge on the O. Now we're not done, because we can start from the original structure and take the lone pair on that central oxygen and push on the pi electrons of the carbon-carbon double bond. This will create an oxygen-carbon pi bond with a plus charge on O, and put the lone pair on the terminal carbon, which will give it a negative charge. If we also try to push that central oxygen's lone pair up toward the O in C double bond O, that will give us the resonance structure we've already drawn, so we're done. There are 3 new resonance structures. In part B, we have a cation, so all we're allowed to do is move that positive charge around. We can't create any new charges. If we use breaking the polar pi bond for C double bond O, the pi electrons become a lone pair on the O, which neutralizes it, and puts a plus charge on the carbon. That's all good. Now that plus charge, which is an empty p orbital, will pull electrons from the carbon-carbon pi bond, and you'll get empty orbital pi resonance, and that will place the plus charge now at the very end carbon. In part C, you have a negative charge, so we can only move the negative charge around. The lone pair on the carbon scares away the electrons in one of the pi bonds of C triple bond N, so we'll end up getting a new pi bond between C and C. We'll break one of the old pi bonds between C and N and push that lone pair onto the nitrogen, giving it a negative charge. In some of our resonance structures, carbon has only 6 electrons and a plus charge, and there's also separation of charge, even when there's an octet on all the atoms. These would be known as minor resonance structures typically, but I like to call them chemically reactive resonance, because they explain the kinds of chemical reactions that the molecule may undergo. Major resonance structures are the way you typically draw the molecule. All atoms have octets, and there are no unnecessary charges, as in the case of the structure shown on the right, which is acrolein. But with chemically reactive or minor resonance structures, what we do is we create charge separation or places where there is less than an octet, and these are reactive centers. So if you look at acrolein at the bottom, its major resonance structure is shown, and we place the lone pairs on the oxygen. Now, if we take the pi electron and move it up to the oxygen through breaking a polar pi bond type of resonance, then we get a plus charge on the carbon and a negative charge on the O. That would be our first chemically reactive or minor resonance structure. That would resonate through empty orbital pi resonance to put the plus charge on the terminal carbon, and that's our second chemically reactive or minor resonance structure. These 2 structures are going to explain some of the chemical reactivity of acrolein, which we'll see in the next slide. Okay, here are our chemically reactive or minor resonance structures for acrolein, with the lone pairs stripped away for clarity. Now we're going to bring in the methyl or CH3 anion, which is going to react with acrolein. This methyl anion can only donate its lone pair where there's the possibility of forming a new covalent bond. So that would be where a carbon only has 3 bonds, that is a plus charge. So that methyl anion could react at the plus charge at one end of the molecule or the other, which is why you see the two arrows going in two different directions. The reaction of the methyl anion at those two different sites could lead to two different products. So that's why two products are drawn where new carbon-carbon bonds are formed between what was a positively charged carbon and the negatively charged carbon. So you see that the methyl is blue and has a new carbon-carbon bond either on the left side of the molecule or on the right side of the molecule. Practice problem 2. Draw all plausible resonance structures and predict the possible products formed from the reaction of compound A with cyanide, Cn-, and compound B with a proton, H+. Make sure that you use the chemically reactive or minor resonance structures to figure out the possible products of the reactions. Answers to practice problem 2. In part A, we can start off by doing a breaking a polar pi bond type of resonance, putting the pi electrons onto oxygen as a lone pair, giving us a negatively charged O and a positively charged C. So there's our empty orbital that can accept a lone pair from the negatively charged carbon of cyanide that makes a new carbon-carbon bond. And that shows our first product. Now, that plus charge also resonates through empty orbital pi resonance and ends up at the bottom of the ring and can accept a pair of electrons again from cyanide to form the carbon-carbon bond in that section of the molecule. So there are two possible products that can be formed from these chemically reactive resonance structures. In part B, we have lone pair to pi resonance. Lone pair on oxygen pushes out the pi electrons onto that carbon atom, giving a plus charge on the O and a negative charge on the C. So now that C is going to be attracted to the proton, and once it protonates, the charge is canceled and we get our product. Notice that I didn't put the proton on the oxygen because it gets a positive charge due to resonance, so there wouldn't be any attraction between the two positive charges. They'd repel. I mentioned at the very beginning of this electron resonance that there is a geometric requirement for orbital overlap to allow resonance to occur. The orbitals that are involved in resonance have to be parallel to each other in order for you to get sufficient overlap. If there is no parallel overlap of orbitals, then there's no resonance. So if you look at the top example, the lone pair on the nitrogen is able to resonate through lone pair pi resonance, and no problem because the lone pair can be parallel to the adjacent pi bond. But in the bottom example, the lone pair on the nitrogen cannot resonate to the adjacent pi bond, even though you think you can draw that. If you look at the actual orbitals, the lone pair on the nitrogen is really perpendicular to the pi bonds that are adjacent to it. So there's no overlap. The lone pair and pi bond aren't parallel. There is no resonance, and so trying to draw that type of resonance would be wrong. Practice problem 3. Which resonance structure or structures is or are wrong due to lack of parallel orbital overlap? Draw the relevant orbitals in your selection or selections to justify your answer or answers. To make sure that you can figure out the correct orientation of orbitals in these molecules, you may want to pick up a molecular model kit to solve these problems. It will really help you understand the geometric orientation of orbitals. It's very difficult to visualize in your head. Answers to practice problem 3. Actually, there's only one answer, and that is that the structure to the right for part B is wrong, because if you draw in the orbitals that are associated with the empty p orbital on the positively charged carbon and the adjacent pi bond, they're perpendicular to each other. Since they're not parallel, there's no overlap and no resonance. So you can't actually show empty orbital pi resonance as is depicted in B.